To analyze a situation like this, one approach we could take would be to choose some particular functions for a and for phi, and then do this integral and see whether or not we can get things to carry through the way we would like them. However, I want to do something a little different. I want to do something that's going to be more general so that regardless of this shape, I will be able to make statements about how the probability would appear, tracking my particle or not. Also, by doing a general analysis, I won't have to assume anything for this unknown frequency, but I can simply get directly to the answer and then engineer what this frequency should be. So I want to take a more general approach than just simply carrying out an integral. Now, this method that we're going to teach you for analyzing such complex integrals. Oh, and the other thing I guess I should really add is if we were to make up some functions here, the integrals that we would have to do actually turn out to be rather nasty. So it's really to our advantage to have a powerful but simple method for analyzing how such integrals behave. And that approach is something known as the method of stationary phase. Now, in order to really draw out how this method works, the first thing that you want to do is to rewrite your integral just slightly into a more simple form. So I want to write my integral psi of x and t. It's going to be mathematically equivalent. I'm going to add up over all my possible wave vectors. But what I want to do is I want to write it simply as a product of a real amplitude, which is this a of k, times a phase factor. So what we're doing is we're taking these quantities, we're substituting in for w, and rewriting the integral as a, and then we're simply going to combine this exponential with the phase factor exponential, so that at the end of the day I will have a of k, I'll have an a of k, multiplying a phase factor e to the I, and I'll call this phase factor phi of k. That's integrated, of course, over all possible k. And you'll excuse me that a came out a little bit uglier than I would have liked. And for us, and for our particular case, it's easy enough to figure out what that phase factor capital phi has to be. We can read it off from our mathematics here, right? So when I bring this exponent times here, when I substitute in, right, I will get I times minus phi of k, and then I will have the remaining factors kx minus omega kt. So this will be minus phi of k plus kx minus omega of k times time t. Now, to understand truly how this integral behaves, it helps to have a diagram of what the integrand looks like. So here's a diagram for the integrand. And I'm going to design a convenient type of a way of diagramming this. So first what we will do is we will have a horizontal axis that represents all the different possible values of k, and I will label my point k0, about which my amplitude is peaked. And then for all the other points, say this point over here, I'm going to draw a picture for, here's a vertical axis right now, right? So this is a particular value of k that happens to be negative. And what I want to do is I want to figure out for that value of k, what is my integrand? Now my integrand in general will be a complex number, so to include that on my diagram, centered on this point, right? At the same point in the diagram where I'm pulling off my k, I'm going to draw a little miniature real and imaginary axis. And I will plot my complex integrand at that particular point. And at that particular point, it will have some amplitude, so it'll look like this, where that length there is a of k. And you'll notice I'm drawing it as a small little vector because I'm far from k0. I don't expect the amplitude here to be large. And it, of course, comes in with some angle. And now I've defined my phase angle here with a positive sign, so this angle here is this angle phi of k upwards from the real axis. Now then, what I can do is I can go to the next point on my line. I can draw another little mini real and imaginary axis, and I can then draw the arrow that I would find there. And in general, I'd find some kind of small arrow pointing, off in some other direction. So as I'm moving along, I have these small arrows. They're pointing in a variety of different directions. And now, at a certain point, I begin to find much larger arrows. So because I'm beginning to approach where my amplitude A was large, peaked near K0. So let me draw, say, one of them down here at maybe 60 degrees downward, right? The next point, maybe it's kind of horizontal. The next point, maybe it's pointing up here at 60 degrees, something like so. And then beyond that, maybe they again are going to start to get smaller, pointing again in various different directions. Okay, so that's the integrand. Now we will try to consider the final integral. So a diagram for the integral. Now the thing to realize about the integral itself is we can think of it, of course, as a Riemann sum, right? For the Riemann sum, what you do is you take a series of sample values of your integrand, just like we've done here. You then add them all together and then multiply by some delta k, right? That's what the integral actually means. So our job then is going to be to draw a diagram where we add up all of these arrows. Now, let's see. So we will have then say, now again, we're talking about the complex plane, and we know actually, how we add up complex numbers. They add just like vectors, so my job in my diagram is to add all these vectors up head to tail. So let's give that a shot here. So, my first vector pointed something like this, and what I have then is a series of small vectors pointing at a variety of different angles. Nothing much interesting is happening as I'm adding these guys up head to tail, right? Where the action really starts is where I hit my longer vectors. And I apologize. In my diagram, I should have made these maybe a bit longer than they actually appear, or maybe had made these here a little bit smaller. So I will try to exaggerate their lengths here in my diagram. So one was down here at like 60 degrees. Maybe he's about this big, right? The next one was horizontal, right? And then the next one was up at 60 degrees, right? And I may then have a series of these that I'm adding. And you can see as I go around here, they're kind of spinning around. So I'm adding them in at all different directions. And then finally, the angles start to get smaller. And, I don't know exactly what they're going to do. They won't make much progress now, though, because they're kind of small. So by the time I've added all of these then, right, my final vector sum takes me from the beginning tail, which was here at the origin, to the final head, right, which was way up here. So this total length here then would be the vector that represents my final integral. Now, I want you to notice something very important here. What I want you to notice is that the different contributions. First, I have a bunch of small vectors that really didn't take me very far, right? Then I came to the vectors that were large, the ones that were near K0, and they kind of added up going around in some kind of a pattern. But because their angles keep changing, right, I really don't make a whole lot of progress. And then I get back into the region where the amplitudes are small, and I make a little bit of progress at the end, but I really don't go anywhere. And so the final end of the day, even though I had some rather large vectors, I don't end up with a particularly large contribution. So what we should ask ourselves is what is needed to get a significant contribution, right? It's good when you think about it that most of the time there's nothing special going on and I don't get very much contribution. I don't get very much for psi, which is simply telling me that most of the time when I'm calculating one of these probabilities, I get something small, right? I want to figure out the condition for getting something big, because when this becomes large, that tells me where my packet is centered, and hopefully I can get that to track my particle. So we need to consider a diagram where we get a significant contribution. So diagram for that would have to have a different kind of a pattern. So I'm going to once again draw such a set of axes. So here's my special diagram, right? Sort of real and imaginary axes, right? And so what I'm going to have, here's K naught. I'm going to have, again, a series of small little vectors. I don't really, it may be different directions. I don't really care what they are doing particularly. But when things get close to K naught, now I really do begin to care. Give myself a little more space here. As I become closer and closer to K naught, I really need my vectors to all begin to point in pretty much the same direction, right? And then, of course, once I get past it, they can begin to spin. When I try to make a diagram now for the integrand, so the now to get the large integral. So this is going to be, I guess, a diagram for a large integral. The trick, you see, was to make sure my arrows weren't spinning here, right? So to get a large integrand, I would start again at some point. Here's my real and imaginary axis. And you can see what happens. I might move around a bit, but the arrows are small, so I'm not making terribly much progress, right? Then I get to a certain point where I get my larger arrows, and the nice thing about these larger arrows is they were all pointing in nearly the same direction. And then, of course, eventually, I'm running out of space in my diagram, we get to where they become smaller, and again, they can start to turn, I don't really care what they're doing because they're not very large, and I end up with a diagram like so. Now, the beauty is, of course, you can see the final tail to head, right? The sum, the vector that gives me the sum here, is going to be a rather large vector, like so, right? Because these were all pointing nearly straight. A much, much larger contribution, and that will then give me the condition that I actually find the peak of my amplitude and therefore the peak of my probability. So let's turn this into a mathematical condition then. Now, there are two versions of the mathematical condition. One is sort of the strict version that will give me the absolute biggest amount, right, that I expect. And then there's a more sophisticated condition which tells me, well, if I'm not in this ideal where everybody adds in a perfect straight line, how much error can I tolerate in having these arrows all lining up? So the first condition is simply to say we do not want the phase changing near K naught. Mathematically, we could say that what we mean then is that the rate of change of the phase, d phi is the phase, with respect to the wave vector, right? We want that to be equal to 0, right? So there's no rate of change. In calculus, right, when we have a function like this where its derivatives are 0, remember sometimes that's a maximum, sometimes it's a minimum. Sometimes it's just a sort of like inflection point. That type of a point is actually called a stationary point, or sometimes a critical point. So this is why it's called the method of stationary phase. We're looking for a stationary point, right, for the phase. Hence the name. Now, we want to be a little bit careful here, though, because notice, I don't care what the arrows are doing when they're small, right? They can be spinning around all they want. They're small anyway. It's only at the point where I've peaked my contributions, right, near K naught, where the weights are peaked. That's where I really care. So this would actually have to happen at K naught. So this is the condition for stationary phase. Now, we can get a little more sophisticated, and it's interesting to consider this and say, well, how stationary do I really need them? And here's a way that we can think about that, right? So you'll notice my wave packet itself was constructed with a set of amplitudes that were peaked, right? But the width of the peak was delta k. So what I really want is the phase at the beginning of this region of width delta k to be very similar to the phase at the end, because I don't care what's happening otherwise. So another way to think of this is to say that I want the phase, right? The change, I should say, in the phase to not be too big, right? And the total change in phase I can tolerate. Well, let's take a look at some diagrams again, right? So here's if we again take an idea or look at our integral. Again, basically we know at the beginning, right, we don't get very far, right? Then we have our large contributions. They start off with some phase, right? And then as time goes on, or as I keep, moving across k, those phase angles are going to be changing, right? And you can see the maximum I get is when all the phases are perfectly lined up, when there is no change in phase. When the change in phase is 0, this is when I get the maximum. But if I take those same arrows, right, and have them bending over a little bit, I won't get nearly as much, and I could be bending to the left, right, or I could be bending down here to the right. I won't get as large a contribution, but I can still get a, reasonably significant contribution. Right? I just want to make sure that what happens is I don't, start arcing around a full 360, because then I've canceled out a lot of where I could possibly end up, right? A 180, again, probably hurts us significantly. But if we're, say, and this is just really an estimate, but if we're, say, where maybe the incoming direction and the outgoing direction are only different by, say, 30 degrees, right? Maybe something more like this, an arc like that, I'm still going to be getting a fairly large contribution, right? That would a diagram like that would correspond to, when I look at where my probabilities are, not the peak value, but somewhere down from the peak, right? So this can give me an idea then actually of how wide my packet is. So I'm very interested in posing a condition like that. Now 30 degrees turns out to be about, so here I'll put, I would really like the change in phase to be 0, but I'm willing to tolerate an error, and remember everything here should be measured in radians, of about 1/2. And that's simply because 1/2 radian is, just roughly speaking, about 30 degrees, right? 1 radian is 57 degrees, so it's, somewhere in that range. So that's the amount of phase change I can tolerate as I go, right, from the beginning of my peak in amplitude to the end of my peak in amplitude. So that's across the width of delta k. So if I want, right, I can divide both sides of this equation by delta k, because now you can see that's telling me what my phase derivative is, right? d phi dk is simply that ratio. And I have to remember to divide all my terms by delta k, and I can divide this here by delta k. And that's simply telling me then, and 0 over delta k is, of course, 0. So this is simply telling me that my rate of change, I would ideally prefer to be 0 to get my maximum. But if I want to know, how much I can tolerate, so I probably write it this way. I want 0. I'll put a little cloud here, because this is when we're thinking about how far off we can tolerate. We're saying we can tolerate being off by plus or minus, and again, this was just sort of an estimate, about 1 over 2 times delta k. Okay, so that's the condition for stationary phase. Let's try to apply it to our case. So for us, what this condition is going to tell us is the following. I want d phi dk evaluated at k0, because that's where I care about these things, right? We know we're going to set that equal to 0, but it's going to be 0 where we are saying, if we want to think about how wide our packet is, maybe a tolerance 1 over 2 delta k. But we can now actually take that derivative. So the derivative that we're talking about, we now have to substitute in for capital phi. And we had capital phi up here for our wave packet. Where'd he go? Right? It's minus little phi of k plus kx minus omega of k times t. So let's repeat that down here. So it's minus this phase that comes from my weights when I'm adding up my integral, plus k times x. That's my dispersion, that's my usual waveform, minus omega of k times time t. And all this needs to be evaluated at k naught. Now, the derivative. Okay, this is pretty straightforward. This is a function of k. The partial derivative of it, well, since it only depends on k, since this one term only depends on k, I just get phi prime. But remember now, it has to be evaluated at k naught for my condition, and k naught is just a constant. So this minus phi prime of k naught turns out just to be some constant. The next term, well, I'm only worried about how things depend upon k, because that's what's determining the behavior of my integral. And so when I take partial derivative of k times x, x is acting like a constant. Take the derivative with respect to k, that just gives me plus x. Final term. Well, this is omega of k times time t. T is just a constant, so I get minus, d omega dk, evaluated again at k naught. So that's some constant value times time t. Now this is great, right? Because now I have something where I can actually solve, I can set these two equations together, right? And I can now solve for x. So let's do that. So to get x, what I'm going to do is I'm going to move all these other terms onto the other side of the equation, where they will combine with my 0, right? And my tolerance, if I want to think about the tolerance. But if I'm just looking for the maximum, they would combine with my 0, and these other terms then would appear with plus signs. So x then will become phi prime of k naught. Interesting, just a constant. Plus the next term is this d omega dk, evaluated at k naught. Another constant times time t. And that's where my maximum will be. If I, again, want to think a little more deeply, thinking about my tolerance, I see here, right, coming from this term, there's also, some range on that, plus or minus about 1 over 2 delta k. Now, we can interpret this, right? What we see is we have x, the peak of my packet, is moving along, right, linearly in time t. It starts at some value when t is 0, and that value we can call x naught. So the original position for the packet is determined by this phase factor in my weights. And this term is giving me then the velocity of the particle, of the wave packet, right? Ultimately, we want that to match the velocity of the particle. But the velocity of my wave packet is this d omega dk, and this should look very familiar to you. This is, in wave physics, simply known as the group velocity. Right? So we've proved, actually, in a very general way using stationary phase, the standard formula for the group velocity. So this is really a nice review of your wave mathematics from 2214 or 2218. And this is a nice point in the course, because now, whichever of those two courses you've taken, we're now kind of on an even footing. We've got a mini review of the key wave physics that we need here for this course. Now, this last bit, remember, tells us how far we can be off of our condition and still get some kind of contribution out of the integral, right? And from this equation, you can see it's telling us how much x actually could vary. So this last term then is telling me the width of my packet, that delta x. So we get all of this now out of our method of stationary phase.